Hi, Matt.
Good afternoon, Michael.
It's good to see you again.
Good. Well, this morning we did combining derivatives and getting sums and products. Now, let's do something really cool, and that is going to be composition. Composition of functions is the heartbeat of how neural nets are constructed.
That's right, because it involves a lot of functions and combined in all sorts of ways, including, very essentially, the composition of two functions.
So let's have a look.
Well, here we have two functions that we played around with last time, so let's compose them. So instead of taking sine of x, I want to take sine of x to the n. So what that means is if you give me a number like 2, I take 2, raise it to the nth power, so it might be 2 to the 10th, which is some big number, and take the sine of it.
And find out the best linear approximation.
So we're going to try to find its derivative. And like you said, we should try to find its best linear approximation. So without even thinking too much about it, we say, well, all we do is take x, add a very small amount h to it, raise it to the power n, and we say, can I do an approximation here?
Well, sure, we did that previously.
So this guy, we know is approximately x to the n plus its derivative, n, x to the n minus 1.
Which we have up there.
That's the derivative, times h, right?
Yep, now this
That
whole...
approximates that, and then I just take the sine.
All right,
what
so
do I
now what are we going to do? So I'll just get you started here. Well, h is really small, and this could amplify the h. But we still want this term to be small, otherwise things kind of break down. So I'm going to call this capital H, and H, capital H, is also going to be small.
Well, so if this number is big like 1,000, how can I make this guy small?
Well, then you make H to be 1 over a million, or 1 over 10 to the 12. You get H small enough so that this capital H is a good increment when we're looking at this combination of x to the n and this piece here.
So you've called this big H. What should I call this guy? Do you want to give it a name?
I'm just happy. No, I'm not going to do that right away.
Okay.
I'm going to say that this is sine of x to the n plus h.
Okay.
We know how to do sine of x, but we've got sine of x as x's argument. Now, if h were 0, we have x to the n. But let's use all that we know already by writing this as u.
Okay.
And then this is going to be plus h.
Now that's starting to look familiar. It's a number plus something little.
And we know how to do this. So I'll pass it on to you.
So we're taking the sine of this guy. And since we're doing approximations, this is approximately, well, I've got my u.
And we've done the model of this before for small h.
That's right. So we know that the sine, the slope is going to be the cosine at u multiplied by big H.
And now, what are we going to do?
Well, so that I don't go off the board, why don't I just remember u is x to the n. So this is sine of x to the n plus, here I have cosine, u was x to the n. And do you remember what big H was?
Yeah, big H was this piece here.
N times x to the n minus 1, all times h.
And we know the coefficient is of h is this stuff in the square brackets.
That's our slope, right?
And but if you look at this, this is product of slopes here, because instead of argument x we had u, so there's x to the n, and this is the slope of this one. And so we've got that the composition function, when you differentiate it, is the product of the other functions working from the inside out.
That's right. So we get the derivative of sine is cosine. We evaluated x to the n, and then we multiply it by the derivative of x to the n minus 1. That's exactly
Of
what
x
we
to
have
the n,
here.
yeah. And so there you go. So in general, we're going to have that the derivative of a simple composition is the product of the derivatives, which is what we've got here, the product of the individual slopes.
And it's always good to point this out. Here we get the product of two derivatives. For the product rule, we had this funny thing. We had a sum of a function times a derivative and a derivative times a function. A little bit more complicated. Here is just a simple product.
I find this quite amazing, and maybe we can use it further. We also can see that this idea of multiplying the slopes in the composition could lead to a very nice graphical picture, which we'll do next time.
Let's go ahead with that.
Good work.
Thanks, Matt.